In this video, I will talk about a new topic which is about material selection for mechanical design. How do we find out the best material for any mechanical design? So this has been a big question since we started designing new things. So whenever we design any equipment or any structure or any machine, we often run into this problem of which materials should I choose? Should I select a metal, or should I use a plastic, or should I use ceramic? So this question is always in our mind whenever we design something new. For every mechanical design, there are two primary requirements: stiffness and strength. So there are many other requirements for our design, for any mechanical design, but these are two primary requirements: stiffness and strength. Every designed machine or any component, any part must have the required stiffness and it must have the required strength. Otherwise, it cannot perform. First of all, we will look at the stiffness requirement and we will try to find out how can we find a theoretical way of selecting a material for the best stiffness. Let us look at this picture, a bicycle. This is a quite old-fashioned bicycle. Still we are using this kind of bicycle. So here, in order to get the right kind of stiffness, many design changes have been done. For example, you can see this is a truss. So basically a truss is to withstand very high load without much of deflection. So this is a rigid structure. In the wheel, we can see there are spokes, and these spokes also have sufficient stiffness so that this wheel does not buckle. Similarly, every part of this bicycle has been designed and the material has been selected such that this bicycle can give a very good performance without any problem with the stiffness. Because if there is a problem with the stiffness, this bicycle cannot be used. For example, if the wheel buckles, obviously this bicycle cannot be used. Similarly, if the frame buckles or any part of the metal, if deforms during the use, then it cannot be used. In this kind of bicycles, you will see that stiffness has been paid very good attention to, and that's why you will see that these bicycles have become quite heavy. These are quite heavy bicycles and difficult to ride. But from stiffness point of view, this bicycle can give very good performance. If we talk about other types of machines, for example, this airplane. The airplane has to fly. It has to leave the ground and it has to fly against the gravity. This kind of airplanes cannot fly unless the stiffness is of the right requirement, because every part of this aircraft has been designed in such a way that it can perform very good in terms of stiffness. And the other requirement for aircraft is, as you know, lightness. For example, the wing must have the right stiffness. It must not be very rigid, and of course it should not be very floppy. This wing has to have the right kind of stiffness. It can bend to some extent, but not too much. The fuselage part is quite rigid, quite stiff, because any movement in the fuselage will lead to some problem in the aerodynamic property of this airplane. Similarly, the landing gears, the engine parts, and the tail parts all have to have very precise stiffness, but with lightness. So this is a special requirement which we did not have to look for in the bicycle. Other kinds of machines or structures, for example, a bridge. So this bridge is a cantilever bridge. This bridge has to have stiffness, the required stiffness, because otherwise the bridge will vibrate when the vehicles pass through this bridge, and in the case of very strong wind, this bridge will oscillate and swing and may break down. So this bridge also has to have very required stiffness, but with stiffness the bridge can also become very heavy, just like this bicycle we were talking about. But if it becomes very heavy, again it will not perform the way it should, because a very heavy bridge will sag because of its own weight. So there is a compromise between stiffness and weight. We want a good stiffness, but we want good stiffness at lightweight, for lightweight. This is one of the most important part of any mechanical design, that the mechanical equipment must have the right stiffness. Lightness in general is an important requirement for most of the mechanical design. The lightweight design concept can provide possibilities of saving materials and energy which are required in the modern context. Energy saving comes from the manufacturing of the product, as less material is needed overall, and also from transportation and fuel efficiency if this product or machine is a mobile one. For example, cars, other vehicles such as in railways or airplanes, etc. But with lightness. So we will look at stiff and light material for cantilever design, and we will try to find out what kind of theoretical analysis we should conduct to find out such kind of material. Obviously, in engineering there are hundreds and thousands of materials available. Out of these materials, which materials should I use for cantilever design? And as you can see that many of the structures that we deal with in engineering do have cantilever type of design. A simple cantilever can be given by this figure. So here this is the cantilever. Cantilever has fixed one end and free another end, and it has got certain length, and the cross section can be a circular cross section or it can be other shapes, for example I section or H section and so on. It can even be a hollow pipe, that is also a cantilever. Now if we apply a force in the cantilever, then this cantilever will deflect, and this deflection has been shown here, slightly high deflection. So delta is the deflection here. So this is the simple design, simple mechanical design that we would like to use for our analysis. Now for this structure, performance limiting parameter is the deflection, because deflection is the something that we do not want to have too much. So a right kind of deflection will be required for this application. So performance can be good if the deflection is within a limit, and the limit will be decided by the design. The deflection is given by this equation. Delta is equal to FLQ over 3EI. F is the load, L is the length of this cantilever, E is the modulus of this material of this cantilever, and I is the area moment of inertia, and is given by pi r to the power 4 over 4. So this is the value of I for this cross section. If we are going to change this cross section to, let's say, I section or H section or hollow section, in that case the value of I will change. So at the moment we will use this formula. So this is the deflection. Now what needs to be minimized and why? If we want to minimize deflection, we can obviously use this formula. We cannot change force because force is decided by the design, the requirement of the design. L also to some extent is fixed, because any structure or any machine, any equipment must have its own dimensions, and we cannot change L much. Then we have got the material property, the modulus, and I. So out of these we can vary them to some extent to achieve lower value of delta. Well, if we fix the material, then E is also fixed. So in that case we can only vary I. But by changing the value of I, we can reduce delta, we can reduce the deflection, but we cannot make this design or this component very efficient unless we make it light. So here the requirement is that it should be light for whatever deflection it has been designed for. So what needs to be minimized and why? In this case, the mass of this structure has to be minimized because that is what we want for the lightness. The mass is given by pi r square L multiplied by rho. Rho is the density of this material. If we combine these two equations, mass and deflection, then perhaps we can find out an equation that can guide us to select the best material for any kind of design which is similar to cantilever. Now you must have seen the bicycles of this type. These types of bicycles are expensive and they are considered more efficient. The reason why they are more efficient is that they can give good performance with lightness. They are very light. So therefore, they are very easy to ride because they require less of energy. So this is the benefit of having something which is light. Still, this bicycle has all the requirements of a good bicycle in terms of stiffness and strength. So the goal is to find out a set of parameters that should be minimized in order to achieve least mass. Now substitute the expression for I in equation 5.1 and rewrite. So we will substitute I is equal to pi r to the power 4 over 4 and we can rewrite this equation, the deflection equation, as this one. Now we rearrange this equation to find out expression for r square. So r square will be given by this expression which comes from this equation. So now we can substitute this r square from here into this equation 5.2, and that gives us mass is equal to pi L. This is the expression for r square multiplied by rho. Rearranging equation 5.5 gives us this one. So finally we get an equation where on the left hand side we have got mass, on the right hand side we have got the design requirements like force and length. Delta is the deflection, which is also a design requirement, and also we have got these two parameters, rho, which is the density of the material, and E, which is the Young's modulus of this material. So this ratio we have got in the form of rho over e to the power 1 over 2. These are the material properties. These are not material properties. These are the design requirements. So rho over e to the power half is known as the material index for selecting the best performing material for a cantilever application. Material index should be minimized. So here in this equation 5.6, you can see that the mass can be minimized if we can minimize this factor, rho over e to the power 1 by 2. Because from design we cannot change this part, so we can only change this part. So if we are trying to select a material for cantilever application and we want the machine or the component has low mass for its performance, for its same performance, in that case we should minimize this parameter rho over e to the power 1 by 2. Or inversely, we can also say e to the power 1 over 2 divided by rho should be maximized. If this is to be minimized, then 1 over material index is to be maximized. And this is known as the performance index for selecting the best performing material for a cantilever application. Performance index should be maximized. So basically they are same kind of parameters. If we write in this form, then it has to be minimized. If we write in this form, then it has to be maximized. And the name is changed to performance index. In this case, the name is material index. Now here we have got some data for some very well-known materials. The value of E in gigapascal and density in gram per centimeter cube. So for steel, wood, concrete, aluminum, and carbon fiber reinforced plastics. For these materials, we can calculate the performance index e to the power 1 over 2 divided by rho, because these are the material values. So we can calculate this, and now we can compare the performance index of different materials. So you will see that carbon fiber reinforced plastics has got the highest performance index, which means that this material can give us the best stiffness for its weight, or we can achieve good stiffness with lightness. After this composite, we can see wood is a very good material for stiffness application because wood can give you very good stiffness with lightness. And this is the reason why we use wood for many structural applications. For example, for roof support, many kinds of woods are very efficient for these applications, and one is the bamboo. Bamboo is a very good material for stiffness with lightness. After wood, we can find aluminum is a good material, concrete and steel. Steel has got very high strength and very good stiffness, but when we make it in terms of performance index, that means how much stiffness it can give for its weight, then steel is not a good material. It is very heavy. For light application, steel should not be used, or we should use steel only for those critical applications where we cannot use any other material. And that's why we can see that in modern aircrafts, steel is being replaced by composites and some of the advanced metals. For example, titanium or aluminum is being used in aircrafts for quite some time. Now, some other things we can also calculate: approximate cost. So for example, if we know the cost of these materials, you will see that carbon fiber reinforced composites are very expensive materials. After that, aluminum and so on. Now we can calculate the ratio of cost per unit performance index. So this will tell us for the unit performance which material is more expensive and which is the cheaper. And you can see that although carbon fiber reinforced composite has very high, very good performance index, but when we consider the cost per unit performance is very, very high. That means this material is extremely expensive. And we can see that wood will be a very cheap material for very good performance. Aluminium is also very expensive material. So we can make a decision if we want a very good performance, but this material will come at a very high price, or we can use aluminium. So this gives us a decision-making tool to decide which material is the best for our application, and depending upon application, we can decide which material we should use, because the cost will always be a very, very important factor. Now, from this analysis, we can plot what is known as Ashby's map, or you can also call it performance map. So we can write the performance index as C. So just now we have found out that this is the index that has to be maximized, E to the power 1 over 2 divided by rho. This is the performance index. Now we can give a value to this. So for any kind of design we want, we can give a value to this. So we can say that our requirement of performance index is C, or any value. Now taking logarithm on both sides, log E will be equal to 2 log rho plus 2 log C. Now this is a straight line if we plot log E as a function of log rho. So a plot of log E versus log rho will be a straight line with the slope of 2, because this is the number 2. The intercept of 2 log C on log E axis will be 2 log C. So this is the intercept and this is the slope of this straight line. We have already calculated performance index for steel, wood, concrete, aluminum and carbon fiber reinforced plastics. So from this data, we can decide what kind of C is good for our design. Whether we want very high C, that means very high performing material, so in that case it should be close to 8, or whether we can manage with lower value of C. As we have seen, that cost is always a factor. If you want very high performance index, then you should be prepared to pay very high cost. Now let us plot this curve: log E on y-axis, log rho on x-axis. So this value of E and rho are material property, so we can get material property for many kinds of materials. Just for an example, let's say our material A is here with certain value of E and it has got certain value of rho. So we take the logs of these E and rho and we can plot this one. Another material B is somewhere here. Material C is here. Material D, material E, material F, and so on. That means on this graph, we can plot all materials that we have. We can plot steel, we can plot ceramics, polymers, and so on. So ABCD basically represents those materials, because as long as we know the value of E and we know the value of rho, we can plot this. Now we will use this equation and we will plot a straight line. So let's say if we have the value of C and slope we already know is 2, we can plot this straight line. So 2 log C is the intercept here. So the value of C will decide this intercept and the slope is 2 for cantilever design. So all the analysis we are doing is for cantilever. So if we have got this line based on whatever value of C we have selected, now we can say which material will be good in terms of stiffness and lightness. Any material which comes above this line are good, can do the performance. That means material A, D, and C. They have got high stiffness and low density or low weight. The materials which are down here are not suitable for this application with the value of C that we have decided. So here the idea is that we should find a material out of these 3 materials which can be used for our application, because all these 3 materials qualify for this application. Now, if we want to isolate one material or very few materials, then what we have to do is to move this straight line even further up. So this movement is something like we are changing the value of C. So now we have got a higher value of C, which is written as C1 here. So we get 2 log C1, which is higher here. The intercept has changed, but the slope has not changed. So this line is parallel to this line. So if we move this line further up, and we can see which material is suitable. So if we move it up, we can say that A is far better than material D and C. And imagine if this line passing through here, we can say that material C is better than D for this application. So this is the way we can do a material selection for any application. In this case, we have used cantilever as an example, but we can do for other applications as well. And we can find out very few material. We can screen out all other materials which are not performing. So we can find out very few materials which are on this side, which are the candidate materials for this application. Now, as I said in the beginning, stiffness and strength are 2 important parameters. But there are many other important parameters as well, which must be taken into consideration. So therefore, it is for any kind of design, it is important that we select couple of materials and then we find out of these couple of materials, which material will do the job best. Because other requirements could be, for example, thermal conductivity or corrosion resistance or heat resistance. These are other important parameters that we have to think about. So therefore, it is important that we select few materials, not just one material. And then we can move on to other analysis. So in this part, we have learned that how to select material for high stiffness and light weight. So here we have got some actual material data. So Young's modulus here, E, and density here. They have been plotted in the log-log plot. So this is in the log form and this is also in the log form. And here are all the materials that we can generally use for engineering applications. So for example, steel, nickel alloys, aluminum alloys are all here. Many of the plastics are here, but plastic composites are up here. Wood can be used in 2 different forms, parallel to the grains and perpendicular to the grains. As we can see that parallel to the grains, they have better modulus than perpendicular to the grains. These are some other materials like foam and elastomers. So just now we have seen this equation for comparing the performance, and C is the performance index, which is given as e to the power half divided by rho for cantilever application. So if we plot the performance index here like this line, and slope of this line is 2, and this intercept will be decided based on what value of C we select. So now we can see that for this application, once we have decided the performance index, we can see that these materials will be good for this application. It can satisfy the requirements. However, in order to find the best material out of these materials, we should move this line up slowly without changing its slope. We can move this line up, and we can find that if you draw an imaginary parallel line to this red dotted line, that we can see that we can isolate some composites like CFRP, and also some of the ceramics can do very good job. But ceramics has some other issues related to fracture, and therefore for many engineering applications, ceramics are not considered good materials. However, for some other application, not structural but non-structural application, they can be a very good material, for example as a cutting tools. So these materials are stiff and they are light. But as I said before, that we should also consider other requirements, not only the stiffness. But as far as the stiffness is concerned, this map can be used to select the best material. And this is known as Ashby Map, or we can also call it performance map. We can see some examples where stiffness of a structure is designed in such a way that we can get very good stiffness with lightness. So for example, these kind of beams, concrete beams in a bridge, is an example of light, weight and stiff structure. For these kind of roofs, also you can see that this is like a cantilever design, and for this cantilever design, it must have the right kind of stiffness, but lightness is also very important. Many modern buildings, airports have got roofs which are very, very wide, and any structure which is very wide will require the right kind of design and right kind of material for its stiffness. So here you can see that this kind of truss and the structure is designed basically to achieve the right stiffness for these roofs. Aircraft wings are very good example how we can achieve good stiffness with lightness. Long ago, before the arrival of modern aluminium, aircraft wings used to be made of wood and some steel structures using wires and so on. These were used to get the right kind of stiffness, but the performance was not very good until we discovered these aluminium alloys. The special aluminium alloys are used for making wing in such a way that it gives the very high stiffness for lightness, and because of this reason, this aircraft, the size of the aircraft is much bigger than the older versions, and it can carry lot of weight. Sometimes materials are also designed in such a way that it has got lightness with high stiffness. This material is a sandwich material. It has got carbon fiber reinforced composites on both sides, and inside it is a foam, is a plastic foam. This kind of structure can give this composite lightness with very high stiffness. Now we will consider material selection for design for strong and light application. As I said before, stiffness and strength are two primary requirements for any design, and most of the calculations are done to satisfy the stiffness and strength requirement. A structure can be stiff, but is it strong? Again, let us go back to the cantilever example. So we will consider this cantilever design, and we will try to find out an index or an analytical way to select the best materials in terms of strength and lightness. So the maximum stress in the cantilever will be given by this equation. In a cantilever, when we apply the load here, the maximum stress will be generated at this point. So this will be the tensile stress, and the value of this will be given by this equation. Sigma is equal to FLR over I, where I is the area moment of inertia given as pi r to the power 4 divided by 4. So again we are using the circular cross section, which has got the value of I given as this. Now substituting I in equation 5.9, we obtain this. So we replace I with pi r4 divided by 4. Now again we write this equation in terms of r is equal to this parameter. So we bring rq on this side, sigma goes on the right side, so you can see sigma here, and total to the power 1 over 3. So this is the expression for r. So we have got this expression for r starting with the stress equation. So we use the stress equation here. Now we will substitute this expression for r in the mass equation. So substituting the expression for r from equation 5.11 in equation 5.2. So equation 5.2 was given as mass is equal to pi r square L multiplied by rho. Rho is the density. So this is the mass of the cantilever. R square will be replaced by this expression 1 over 3. So here we get 2 over 3 L rho. So this is the equation for mass of the cantilever. Now replacing sigma by sigma y. Sigma is the stress. So the maximum stress the material can withstand is the yield strength of the material. So we were talking about the point where the maximum stress will be experienced. The stress can go as high as sigma y. So we can replace sigma by sigma y, which has been done here, and these material properties has been separated. And these are the design requirements, for example load and the length of the cantilever. And these are the material properties, rho and sigma y, which is the yield strength of the material to the power 2 over 3. So from the strength requirement, we can say that rho over sigma y to the power 2 over 3, this is a material index, and this should be minimized in order to get lower mass. So let us see the value of the material index for some materials. So here we have cast iron, aluminum alloy, steel, PVC and magnesium alloy. These are the density values and the yield strength. Here we have got converted into performance index, that means inverse of this one, which is sigma y to the power 2 over 3 divided by rho. So as I said before, if material index is to be minimized, then inverse of this, that is performance index, should be maximized. So if we calculate performance index for all these materials, these are the values. Out of these, the material which has got the maximum value of performance index would be the best material in terms of strength and lightness. So here we can see that magnesium alloy is a good material. After that, aluminum alloy tends to perform quite well. Cast iron, steel has got very similar values, and PVC also is not good in terms of strength and lightness. So this is an index which can be used to compare different materials and find out which material will give us good strength for lightness. So material selection for high strength and lightweight application for cantilever using the Ashby's approach. So again, this was also developed by Asbhy, and that's why this is also known as Ashby's approach. So just like before we did, performance index is this one. We give a value of C. So we call it performance index of C, which can be decided by the design. So now taking log on both sides, we can say log of sigma y is equal to 1.5 log rho plus 1.5 log C. So in this equation, if we plot log of sigma y and log of rho, then that equation will be a straight line with the slope of 1.5 and the intercept of 1.5 log C. So here are the data for actual materials. The strength sigma y. So when it is a ductile metallic material, then it is sigma y. When it is a brittle material or a composite, we call it fracture strength. So sigma F is written here. Density, both are in logarithmic plot. And since these are material property, we can get the data for all the materials and we can plot them here. So these materials have been grouped together. So these are ceramic materials and diamond is also here. Composites, polymer-based composites, metals, the engineering metals, plastics, engineering polymers and other types of plastics, elastomers, foams, wood, and so on. Now here we can plot this performance index, that means this equation. So as I said, the slope of this equation is 1.5, which is plotted here. Same equation has been also plotted here with different values of C. So here you can see that any material which is above this line is good for this application if we decide about the value of C. However, if we want the best material in terms of strength and lightness, what we can do is to move this line up without changing its slope, and then we can isolate some materials which will be the best material in terms of strength and lightness. So again, in this case, we will find that CFRP or GFRP, the composites, will be the best material. Even wood can perform better than some of these metals. If you imagine a line parallel to this passing here, you can see that wood has got better strength for lightness than many of the alloys. Again, ceramics are also very good in terms of strength and lightness, but because of their fracture properties, they will not be selected for any tensile application. However, they are good for compression, for compressive applications. So we can see that using this approach, the Ashby's approach, we can find out the best material for any kind of mechanical application. In this example, we have used cantilever as one of the structural member, but we can have other kinds of application. We can have tie rod, we can have 3-point bending, and so on. So in each analysis, this part, the performance index part, will change. And depending upon this performance index, we can find out that this straight line will have different slope. For example, in some cases, this will be the slope, while in other cases, this will be the slope. So by changing this slope, we can see that the material which will be the best for this application will change to some extent. Now, specific modulus divided by rho or density is known as specific modulus, and specific strength, fracture strength divided by rho or density, is known as specific strength. So for all materials, we can calculate the specific strength and specific modulus, and we can plot on this type of graph. So here you can see all materials are represented. So these are group of materials like ceramics, steel and other metallic materials, polymers, composites, and elastomers and polymer foams. Now if we find out the best material for best application, we need very high specific strength. That means the material should be very high strength for its weight, and specific modulus should be high as well. So the best material will be in this corner, where we get the best in terms of specific strength and best in terms of modulus. Again, we can see that ceramics are very good high performing materials, but as I said, ceramics have the problem with fracture. They are not applicable for tensile application, but for compressive application, they are very good materials. After that, we can see that steel and nickel, fiber reinforced composites, these are very high performing materials. Nickel alloys are also considered very good materials. The plastics are not very good in their pure form. So the plastics can be good material in the form of composites, but in their pure form, they are not very good for structural application where we need high specific strength and high specific modulus. Similarly, elastomers and polymer foams are not very good in terms of these requirements. On the other hand, however, if your concern is to find out materials which are of lower specific modulus or lower modulus and lower strength, then you might focus on this side. So in this case, materials are not of lightweight, but some other properties might be more important than lightness. So it all depends upon our requirements, whether lightness is important or not. But for many of the applications, like structural applications or applications where the machine is going to be on the mobile, for example, transportation or aircrafts, in this kind of application, you will always find that the materials must have lightweight, must be of lightweight. So it depends upon our requirements. In this video, we have discussed how to consider two important properties like stiffness and strength for any kind of mechanical application when lightness is very, very important, and how we can use Ashby's approach to find out which material would be the best for your application in terms of stiffness, strength, and lightness. Finally, I would like to come back to this example of bicycles I have used before. So if you see this bicycle, which is old-fashioned, and this bicycle which looks quite new design, there are some differences, but there are a lot of similarities. As far as the basic design is concerned, they are quite similar. So the truss is still in the same way that has been used in this one. The fork, the wheel, the spokes, there are a lot of similarities. But in order to reduce the weight of this bicycle, many things have been removed. So there is no rear rack, there is no the chain guard, or there is no fender in this bicycle. So these can reduce the weight, but not much. In order to get further reduction in the weight, the material has been changed. For this, we need to have the efficient design of material, and this is where our analysis of material selection comes into. In order to select the best material which can be stiff, strong, but light. So that means it should complete all the functions. It should provide all the functions with lightweight. And for that, we need to conduct the analysis and find out the best material. So we have found from our analysis that the best materials are carbon fiber reinforced composites, or it can be aluminum or titanium alloys. These are the very efficient material in terms of lightweight but good stiffness and strength. So this is how we can conduct the analysis and improve the efficiency of any product or any machine that we have. So with this kind of changes in the material and some changes in the design, we can make this bicycle much more efficient, because this will be very easy to ride compared to this one. I would like to show you this picture which I took with Professor Asbhy in Singapore in 2016 during one of the materials symposium that Professor Asbhy organizes. So it was a rare opportunity for me to meet Professor Asbhy, and this is the picture with him. Finally, I would like to summarize. Material selection is an important step in the process of mechanical design and manufacturing. Stiffness and strength are two design requirements that should include lightweight consideration right at the early stage of design. For both stiffness-based and strength-based designs, the performance index can be calculated, and several materials can then be compared using Ashby Map for a particular design. Lightweight mechanical design can bring benefits in terms of less material requirements, low manufacturing cost, energy savings at many stages, and fuel efficiency for mobile applications such as automotives, railways, and aircrafts. Thanks for watching this video. If you have any question or comments, please do write them down below in the comment section.